Hello everyone and welcome back to Greenstack Hydrogen webinar series. It's wonderful to see many of you joining us today from the different part of the world. Thank you for taking time to be here with us. I'm Prasadini Wickramasinghe. I'm an energy analyst and I coordinate our activities at Greenstack Hydrogen in Sri Lanka. First, I would like to warmly welcome our esteemed speaker for today's webinar, Sonia Pérez. Sonia is a product manager for Gexcon EFFECTS and RISKCURVES software, leading the development of advanced consequences and risk modeling tools for assessing accidental chemical releases. With a background in chemical and process engineering and over a decade of experience in process safety, Sonia is a recognized expert in fire, explosion, and dispersion modeling. She has contributed extensively to module development, scientific publication, and validation studies, ensuring the accuracy and reliability of safe assessments. As the Effect and Risk Curve product manager, Sonia plays a key role in aligning product innovation with industry needs, acting as the bridge between marketing, sales, research, and development and customers. She actively engages with industry professionals through training, webinars, and technological workshops, helping organizations enhance safety and energy transition and high hazard industries. This is actually Sonia's second time collaborating with us for a webinar. The first session was held in 2024 and you can still access the recording via our Greenstack website or our YouTube channel. Sonia, thank you for accepting our invitation. And again, without further ado, let's dive into today's session. Sonia, the floor is yours.
Thank you so much, Prasadini, and thank you for the introduction. Well, first of all, hello everyone, and welcome to today's webinar. Thank you so much for everyone's time to join us today. I'm very excited to show you how Gexcon's consequence and risk modeling tools, EFFECTS and RISKCURVES, can support hydrogen hazard modeling, which can help you design and operate more safely and with more confidence in the hydrogen space. So let me get started with just a bit of a structure for today's webinar. I will first start with a quick introduction to Gexcon, followed by an introduction to why hydrogen is such an important fuel. And I will continue with hydrogen safety challenges and introduce you to EFFECTS and RISKCURVES, which are Gexcon's software modeling tools that can be used for hydrogen hazard and risk assessment. After that, I'll walk you through a practical case study using these software tools to assess different hydrogen hazards. And as Prasadini mentioned earlier during the introduction, we will finish up with a live Q&A. So feel free to drop your questions in the chat as we go, and I'll make sure to answer as many questions as we have time for at the end of the session. And if we don't have time to respond to all the questions, feel free to reach out to us so we can provide further clarification or just continue those conversations. So let me get started with a quick introduction to Gexcon. As many of you may already know, Gexcon is a global company specializing in safety and risk assessment, particularly in the fields of fire, explosion, and dispersion modeling. We are supporting organizations worldwide by combining expert consulting, advanced modeling software, including FLAGs, EFFECTS, and RISKCURVES, as well as large-scale fire and explosion testing. All of our software tools are grounded in decades of real-world data and scientific research, and they are used across industries to model hazards, assess risks, as well as to plan for safe operations. So everything we do is focused on helping our clients protect people, assets, and the environment. All right, so with that being said, why are we all talking about hydrogen? Let's just take a look at why it matters and the role it plays in the future of our energy transition. So hydrogen plays a central role in helping us decarbonize sectors that are hard to electrify, like heavy transport as well as industry. So hydrogen has the highest energy density by mass of any fuel, making it extremely efficient. Also, when used in fuel cells, hydrogen produces only water as a byproduct, making it a clean energy source with zero emissions at the point of use. It's also a very versatile chemical, as it can be used to store energy as well as to power vehicles, heat industrial processes, and serve as feedstock in sectors like refining and ammonia production. In fact, hydrogen is already in high demand as an industry raw material. And that demand is only expected to grow as countries invest in cleaner technologies and hydrogen-based fuels. So while hydrogen has all of these advantages, its unique properties also pose safety challenges. Therefore, production, storage, and use of hydrogen needs careful safety planning. So how abundant is hydrogen? Well, hydrogen is actually the most abundant element in the universe. It makes up for about 75% of the universe's elemental mass. But on Earth, it's not quite as dominant. It only accounts for about 0.03% of the Earth's mass, and that's because it rarely exists on its own. It's usually bound up in compounds of water or hydrocarbons. Still, it's estimated that we have around 1.8 trillion metric tons of hydrogen here in Earth. So the issue isn't really whether hydrogen is available. The real challenge is producing enough clean hydrogen to meet future energy needs. According to the International Energy Agency, we will need around 530 million metric tons of hydrogen annually by 2050 to stay on track for net zero goals. So that's a huge leap from today's production levels, and also a major driver behind current investments and innovation in hydrogen technologies. Which takes me to the very important fact that hydrogen can be produced in several ways, and the carbon footprint varies significantly depending on the method. Brown hydrogen, for example, comes from coal via gasification, and it comes with very high CO2 emissions. Gray hydrogen is produced from natural gas and is currently the most common form of hydrogen, but it also releases CO2 into the atmosphere. Blue hydrogen is similar to gray, but CO2 emissions are captured and stored using CCUS methodologies. Then we have white hydrogen, which occurs naturally underground. And this methodology is still in the early stages of exploration, but it's generating a lot of interest for future potential. Green hydrogen, on the other hand, is the cleanest option for hydrogen production. Hydrogen is produced via electrolysis of water using renewable energy sources like wind or solar. Pink hydrogen uses nuclear energy to drive water electrolysis. So this is an important realization that not all hydrogen is created equal, and reaching net zero will depend on how quickly we can scale up low emission hydrogen production methods. So it is clear that hydrogen has a lot of potential, but it also comes with some unique safety challenges that we need to address, which is the main focus of today's webinar. So just to give you a bit of a run through the different unique properties for hydrogen. Hydrogen is extremely buoyant. So hydrogen gas typically rises up quickly, but in its cold liquid form, it can behave like a dense gas as well. Then liquefaction requires extremely low temperatures, near absolute zero, so near 0 Kelvin, which makes storage and transport quite challenging. Hydrogen is very reactive and has a very wide flammability range, which means that it can ignite in a wide range of concentrations in air. Hydrogen's laminar burning velocity is around 8 times faster than most hydrocarbons, increasing the likelihood of a transition to detonation. It requires very little energy to ignite, and it can auto-ignite at high pressures. Additionally, the hydrogen flames are actually nearly invisible in daylight, posing certain detection challenges, and it can cause material embrittlement. So selecting the right material for hydrogen storage or handling in general is quite essential. So it's because of all of these unique properties that handling hydrogen safely means more than just care. It also requires a deep understanding of its behavior under different conditions. And that's where hazard modeling comes in. Hazard modeling helps us predict the potential consequences of industrial accidents. So we can use hazard modeling for designing safer facilities, setting safety distances between equipment or between industrial facilities and urban areas, as well as to implement mitigation strategies such as ventilation, fire suppression systems, or physical barriers. So depending on the hazard type, we apply different modeling approaches. We have fire modeling, explosion modeling, and dispersion modeling. Fire modeling evaluates thermal radiation. Explosion modeling estimates overpressures and shockwave propagation. And dispersion modeling simulates the spread of toxic or flammable gases. So it's with all of these insights that we can understand the potential impact. And that's what brings us to the next question, which is, how likely are these events to occur? And that's where the concept of quantitative risk assessment, or QRA, comes in. QRAs typically consist of two different parts. We have consequence modeling and risk modeling. Consequence modeling predicts what happens if a hazardous release occurs. So it estimates the effects of fires, the effects of explosions, or the effects of gas dispersion on people and infrastructure. So it helps design safer facilities through prevention and mitigation. So that's the first step. But then, while consequence modeling tells us what could happen, risk modeling assesses how likely these events are, combining likelihood and consequence information. So typically, risk modeling uses failure frequencies, weather data, and probabilistic information about people, operations, and system reliability. So together, consequence and risk modeling can help determine if the risks at a facility meet safety regulations and whether that risk can be considered acceptable, or if it's not acceptable, it informs decisions on which are the best prevention or mitigation strategies. Now that I've covered consequence and risk modeling, let's see how to make the whole process faster, easier, as well as more reliable. So using dedicated software tools like EFFECTS and RISKCURVES, you can really streamline this quantitative risk assessment, which will save you time and will lead to more accurate results. EFFECTS and RISKCURVES are advanced modeling tools developed by Gexcon to support hazard and risk assessments. And they are both built to handle complex calculations while providing clear, consistent, and transparent results to support safety decisions. The main difference between one and the other is that EFFECTS focuses on simulating the physical effects of accidental releases like fires, explosions, and toxic dispersions, and translates these into potential impact on people and infrastructure. RISKCURVES, on the other hand, takes those results further by performing full quantitative risk assessments using a range of risk metrics to quantify the overall risk. EFFECTS is commonly used for preliminary consequence assessments, sensitivity analysis, supporting process hazard analysis, and it plays a key role in compliance reviews, facility siting, and even incident investigations. RISKCURVES is typically used for more advanced probabilistic studies, including full QRA studies, alarm demonstrations, emergency response planning, and preparing safety cases for regulators. So together, they help organizations make well-informed decisions on risk reduction, design, and urban planning near hazardous facilities. So these software tools are used in industries where hazardous materials are handled. So that goes from oil and gas, refining, petrochemicals, even to chemical manufacturing. And they are also vital in the energy transition, as we've adapted our models to support emerging technologies and chemicals like hydrogen, ammonia, battery energy storage systems, as well as CO2 in the context of carbon capture and storage. So our mission is to enable a safe decarbonization, protecting people, assets, and the environment, while helping deliver reliable and affordable energy for both industry and society. So as I mentioned, these tools are widely used in industries handling hazardous materials, and they are especially important nowadays as we transition to low carbon technologies. One example, which is the main topic of today, is hydrogen. So as fuel cell vehicles become more common, hydrogen refueling stations are becoming key to cleaner transport. So just to give you a clear picture of how that looks like, I'll now walk you through a practical case study on hazard evaluation at a hydrogen refueling station. This will show you how EFFECTS and RISKCURVES can help in identifying risks and support safer design operations for this specific use case on a hydrogen refueling station. So just like petrol or diesel vehicles, hydrogen fuel cell vehicles are refueled at purpose-built hydrogen refueling stations. A typical refueling station includes storage tanks for compressed hydrogen, compressors to pressurize the gas, a pre-cooling system to ensure safe and efficient fueling, a hydrogen dispenser where the vehicle is refueled, as well as transport, as hydrogen is delivered to the station by road. So understanding how these components work is key for identifying what are the potential safety challenges. So let's look at these different challenges on a hydrogen refueling station. So for this particular case, some common hazards at a hydrogen refueling station include leakage from storage tanks due to mechanical failures or poorly designed joints and fittings, pipeline leaks, particularly in high pressure sections, risks associated with compressors, such as internal explosions or leaks from worn seals, and leaks during vehicle dispensing, often caused by improper procedures or insufficient inspection. So if not properly managed, all of these hazards can lead to serious accidents. So building on these different hazards that I just covered, it's important to understand how compressed hydrogen is handled at refueling stations. So in these hydrogen refueling stations, it is supplied high purity, high pressure hydrogen fuel to two main vehicle types. There's light duty vehicles like passenger vehicles, and there's heavy duty vehicles such as trucks and buses. Typical operating pressures differ. So for passenger vehicles, for example, these usually have 700 bar composite tanks holding about 5 kilograms of hydrogen. And they are equipped with a 2 millimeter pressure relief valve, meaning any accidental release would leak through a 2 millimeter opening. Buses and trucks use tanks at 350 bar, storing up to 50 kilograms of hydrogen with a 4 millimeter pressure relief valve. When it comes to hydrogen distribution, compressed gas is transported primarily by tube trailers. So most of these tube trailers have 10 cylinders pressurized at 200 bar, each with a 2 cubic meter capacity. Then we have carbon fiber composite cylinders, which are also common. And these are arranged in vertical packs, storing up to 500 bar with about 350 liters of hydrogen each. Then we also have cylinder packages, which can include multiple bundles. For example, they're typically transported in 16 packages holding 27 cylinders, each at 200 bar. So a very common hazard at the hydrogen refilling station is a leak during unloading from the delivery truck. This can happen if the delivery hose fails, causing high pressure hydrogen to escape. To simulate this accurately, we need a few key details, specifically around operating conditions. So the hydrogen in this particular scenario is stored in composite cylinders, which, as I just said, the operating pressure is usually around 500 bar. Each of these cylinders holds about 350 liters of hydrogen, and the leak would come from a 10 millimeter hose. So these inputs can help us simulate the potential effects and evaluate the risk of the scenario. So we know that there's a release of hydrogen through a cylinder that contains 350 liters of hydrogen at 500 bar, which is released through a hole of 10 millimeters. When modeling a hydrogen leak, one of the key steps is to understand what could happen next. What are all the potential loss of containment events? And that's where an event tree comes in. So what you see in this event tree here in the slide is event tree for a hydrogen release. So in this case, the hydrogen release is due to a leak from a damaged hose during the unloading of a truck dispensing hydrogen to a hydrogen refueling station. So from there, several outcomes are possible, depending mainly on if and when the gas ignites. First possibility is that there's no ignition, which is what you see at the top of the event tree. What happens is that the hydrogen simply disperses into the atmosphere and there's no hazard. Second possibility is that we have the immediate ignition of hydrogen, which can cause a jet fire. This jet fire is a high velocity, high temperature flame that follows the path of the leak. And the third option is delayed ignition. So the flammable cloud of hydrogen doesn't encounter an ignition source until it's dispersed along wind for a little bit. So we have a generation of a flammable hydrogen cloud that it ignites a little bit after it's been released. And the consequences of this event depend on the environment. So if we have an open, unconfined space, the cloud may ignite as a flash fire, which is a fast-moving flame that can cause burns through thermal radiation. The other possibility is that in a confined or congested area like pipe racks, machinery, or even walls, the ignition can lead to both a flash fire and a vapor cloud explosion that produces overpressure that risks structural damage. Each possible path in this event tree must be carefully considered in consequence and risk assessments, which is the reason why I'm sharing this one today. So tools like effects and risk curves can help us quantify the impact of each of these scenarios. So hydrogen jet fire, hydrogen flash fire, hydrogen vapor cloud explosion. To evaluate the potential outcomes of this specific hydrogen release, I will use effects and risk curves. Effects to simulate the physical consequences, like as I just said, hydrogen jet fire, a gas dispersion, and a potential vapor cloud explosion, and risk curves to move from consequence to risk modeling. So I will use risk curves to quantify how likely each outcome is to happen and who or what could be affected using risk metrics such as location-specific individual risk, ERPA, consequence risk, and societal risk. So together, these tools help us go from what if to how likely, because ultimately what we want to know is how we can design a safer facility or safer operations to ensure that we can either prevent accidents from happening in the first place or mitigating their effects. So let me start using effects to simulate these different physical effects. This way you can see what is the heat radiation from hydrogen jet fires, what is the overpressure levels from a hydrogen vapor cloud explosion, and what's the concentration in a hydrogen flammable cloud for this specific scenario that I've just defined. So let's first focus on the immediate ignition branch of event tree. So if we have hydrogen being released and encounters an ignition source straight away, this results into a jet fire. And this event is especially dangerous because jet fires can deliver intense thermal radiation, and they are directional, following the momentum of the gas, and they can persist as long as the release continues. What you can see over here is a jet fire simulation using effects. This can help us understand the size, the shape, and the thermal impact of a hydrogen jet fire under the defined operating conditions. When I outlined the different properties of hydrogen, one of the things that I mentioned is that a key feature of hydrogen jet fires is their low emissivity. That's what makes the flame almost invisible in daylight conditions. What happens is that hydrogen emits less thermal radiation than hydrocarbons like methane or propane. And in fact, there's several experimental data that shows that hydrogen flames typically don't exceed like about 70 kilowatts per square meter in surface emissive power, whereas other hydrocarbons can reach surface emissive powers that are above 300 or 400 kilowatt per square meter. So this is reflected in this effect simulation. So what you see here is that the thermal radiation footprint is especially concentrated near the release and drops off more quickly with distance than a comparable methane release. And as expected, the surface emissive power within the flame stays within or below the 70 kilowatt per square meter. So it's accurate to what's expected in reality. So this type of result is extremely valuable for safety engineers and designers, because by looking at the results of this jet fire, we can answer questions like, how far should people and equipment be from potential leak points? What kind of passive fire protection is needed for nearby structures, as well as with what emergency response measures are appropriate for a flame that's hard to see in daylight. What you can see here is the evaluation of how release orientation affects the jet fire behavior, also simulated with effects. So what you can see is that a horizontal jet fire travels farther and has a more extended thermal footprint, whereas a vertical jet fire rises rapidly with a shorter reach due to buoyancy effects, and a 45-degree jet fire behaves somewhere in between. So these differences are important for assessing things like flame impingement, planning equipment layout, and designing effective fire protection measures. So for instance, one of the most common protection measures is firewalls. So you could use this type of information to help design such firewall, like where would it need to be placed and what would be the required height of such a firewall to ensure that it's blocking the effects of a jet fire. Because this is a side view of this jet fire scenario, whereas the previous one is a top view of a jet fire scenario where we see the release of the hydrogen refilling station. This structure over here is a regular refueling station, and there's some shops around in here. So the lowest surface emissive power of the jet fire can actually reach those areas. So it's very valuable information for design and safety purposes. Now, let's look at another possible outcome, which is the delayed ignition. In the case of delayed ignition, hydrogen leaks and disperses, forming a flammable cloud. If that cloud encounters an ignition source before dispersing completely, it ignites as a flash fire, which is a fast-moving flame front that follows the cloud. In this simulation over here, what you see is the side view of a hydrogen jet and how it behaves in slightly unstable atmospheric conditions. So this is specifically for stability class B3. So atmospheric class B, which is slightly unstable and wind speed of 3 meters per second, which corresponds to a moderate wind with some vertical mixing. So what we see from the simulation is that initially the high pressure release keeps the jet low and very close to the ground for the first approximately 40, 50 meters. But as momentum drops, the buoyancy effects dominate this hydrogen cloud, which is what's causing the plume to rise rapidly. So from a safety perspective, this type of behavior has important implications because gas detectors, for instance, they should be placed low at the ground near the release point, but also consider accumulation under ceilings or overhangs where this rising hydrogen cloud could ignite. Something very, very important is that hydrogen isn't always buoyant. There is the typical misconception that hydrogen will always rise up, but it's not always the case. The behavior depends on atmospheric stability, wind speed, release pressure, and momentum. So the previous simulation was for B3 atmospheric conditions, and this one is for D5. So atmospheric stability D, which is neutral, and wind speed of 5 meters per second. So it's a slightly stable atmosphere with low wind. And what happens here is that the hydrogen cloud actually remains near the ground for a lot longer. And this increases the risk of ground level ignition or accumulation in depressions because we don't see any rising behavior for these specific weather conditions. So that's why simulating these scenarios is crucial to understand how to design safe facilities and prevent incidents, because we not always have rising clouds of hydrogen. Under certain conditions, they can also stay close to the ground. So you still have a very likely possibility for like encountering an ignition source, and with the very wide flammability range for hydrogen, it will most certainly create a flash fire and potentially a vapor cloud explosion. Now, if the flammable hydrogen cloud drifts into a congested or a confined area, ignition can trigger not only a flash fire, but also a vapor cloud explosion. So as I explained earlier, this hydrogen release occurs at a refueling station, which is this one over here. It's just located a few meters away from a conventional fuel station. And this regular refueling station actually introduces a critical hazard, and is that the roof of the regular refueling station creates a confined corridor between the ground and the ceiling, which is an ideal geometry for trapping a flammable cloud. This setup can significantly increase the risk of detonation, as it restricts vertical cloud dispersion, promotes turbulence upon ignition, which ultimately amplifies overpressure. So let me show you a simulation to illustrate how this layout affects a hydrogen vapor cloud explosion. So what you see in this other simulation over here is a flammable hydrogen cloud, which is forming near the unloading area. So this remains a hydrogen refueling station. And that's where the transport trailer is parked. So it helps us see how far the cloud spreads in all potential wind directions, and whether it reaches the congested area of which is this nearby gas station. And we can assess the hazard using different flammability thresholds, like the LFL, lower flammability limit, which is the minimum concentration needed for ignition, as well as the 50% LFL, where ignition is still possible, and 25% LFL, which is a conservative boundary used for safety planning. This other simulation shows the dynamic behavior of the flammable hydrogen cloud, which moves and spreads into the congested area. So tracking the cloud over time reveals how quickly and how far it disperses. So in this case, we see an overlap of the hydrogen flammable cloud with this gas refueling station, which is the red geometry over here. So these insights are, again, key for emergency planning and for placing gas detectors strategically to help prevent ignition. These are the simulation results of the hydrogen vapor cloud explosion, showing the estimated overpressure effects. And in this case, the explosion occurred because the flammable cloud was trapped under the roof of the nearby regular station. So what EFFECTS allows you to do is define 3D congestion zones directly on the map. So you can draw the congestion area in the map, specifying what's the blockage ratio, the obstacle size, and the height of this congested area. So then the software can calculate how much of the flammable cloud overlaps with the congestion area, and uses the trapped mass and its volume to estimate the explosion strength more realistically. So now that we've assessed physical consequences with EFFECTS, we can use risk curves for quantitative risk assessment. So as I mentioned before, risk curves is used to quantify risk. So it's to give risk a value so that we can numerically determine whether the risk is acceptable or not under safety regulations. And there's different risk metrics that can be used to quantify risk. basically we have location-specific individual risk, air path, societal risk, or consequence risk. And what we'll do here is that riskers will quantify risk by integrating failure frequencies, ignition probabilities, meteorological data, as well as population exposure. So yearly weather data, including wind speed, wind direction, and atmospheric stability, is used to simulate dispersion accurately. And actually not only dispersion, but also events that are affected by wind, like jet fires and pool fires. So what you see with these wind rows over here in the left side of the slide is that you can define in risk curves your own meteorological distribution. You can specify the probabilities for various wind speeds, wind directions, and stability classes. And you can also define nearby population areas. And that's what you see in this map in the right, which I've also extracted from risk curves. Again, the hydrogen refueling station is over here, and there's different population areas. There's the regular refueling station, so there's a shop, and there's a dispensing area, so there will be people, there's shops, there's a residential area here in the south, restaurants in the north, and apartments in the west. So all of these population distribution can be used by risk curves to calculate societal risk. And this is the type of approach we would use to determine whether risk is acceptable or if further safety measures are required. Now, let me explain the different risk metrics calculated in risk curves and the results produced in this QRA study. First of all, we have location-specific individual risk, which is the annual probability that a person outside the facility is fatally affected by a hazardous event. And this metric assumes that the person is unprotected. So that means no shelter, no protective gear. That's also a reason why location-specific individual risk is actually a very conservative estimate, because people usually spend time, like limited time outdoors or limited time in certain areas, like they move around different zones. What we see in this simulation result over here is the total location-specific individual risk for the hydrogen refueling station, which cover all hazards and all leak scenarios modeled in EFFECTS. That includes all jet fire possibilities, paper cut explosions, etc. So while criteria vary by country, vulnerable developments like apartments, hospitals, and schools are generally not allowed inside the 10 to the minus 6 risk contour, which is, as you can see, the orange shaded area. So there's no vulnerable areas allowed within the orange shaded contour. What you can see here is that this orange contour actually extends to the regular gas refueling station. And there are shops located here in the east, but this contour doesn't reach it. And there's a residential area south from the refueling station. And the 10 to the minus 9 contour does reach this area, but that is usually acceptable. So it's not within the orange contour. So I said that location-specific individual risk might be quite conservative. And that's the reason why ERPA is typically calculated as well. So this offers a more realistic risk assessment by accounting for building occupancy and protection measures. So it supports better safety and emergency planning. Calculating ERPA involves defining occupied buildings, number of people, what are their roles, what are their movement patterns, and their protection factors. So what ERPA simulates is where each role spends their time throughout the day. There are different ways of presenting ERPA based on the occupied building or the defined role. So let me show you how to interpret these results with an example. So going back to our use case, and let's evaluate ERPA around the hydrogen refueling station. There are two main areas with people that could potentially be exposed to the hydrogen release due to this failure in the delivery hose. There's a regular, like the gas station shop, and the refueling area. In the shop, let's assume there are 10 people present 50% of the time with protection. And in the refueling area, there's one person present 50% of the time without protection. RISKCURVES allows you to define specific roles and occupancy patterns. So a customer could spend, let's say, 6 minutes per day in the shop and 12 minutes a day in the refueling area, whereas an employee of the gas station works 7 hours per day in the shop and is at the refueling station for 2 hours a day. So this information is essential for calculating ERPA, which accounts for both exposure time and protection levels, leading to a more realistic risk assessment. So once those roles and buildings are defined in risk curves, ERPA can be presented in risk curves in different ways. So first of all, ERPA can be calculated for each occupied building. So in the context of our use case, an occupied building or an occupied area would be the shop at the gas station and the refueling area. For each building, you define the number of people present, their presence factor, and their protection against fires, explosions, and toxic releases. And these results include ERPA for individuals within that building, potential loss of life calculated by multiplying ERPA for that building with the number of occupants, a risk ranking report showing the most significant contributing phenomena to each of those buildings, and a geographic risk grid, which highlights building-specific risk on the map. This can provide a clear understanding of which areas of the facility pose the highest risk to occupants. The second method presents ERPA based on employee roles. In this context, that can be customers and they can be employees. And each of these roles has a different risk profile depending on their movement throughout the facility and the time spent in each location. So what the results show is ERPA per role based on their daily routine and location exposure, and a risk ranking, identifying which buildings contribute the most to each role's risk. The third option is the ERPA summary report, which brings everything together. So this report provides a high-level overview of this individual risk per annum across the facility, which brings together results from both previous methods. We have a building level summary of ERPA and potential loss of life, and a role level summary showing how each employee group is exposed across the site. So it's this consolidated view that supports the high-level decision-making required to help prioritize safety measures for both people and infrastructure. One of our newest functionality is that this ERPA summary can now be visualized geographically on a map, which is what you see in this slide, which makes it a lot easier to identify high-risk areas spatially and geographically in the map, communicate risks more effectively to stakeholders, and visually guide where improvements are most needed. So this map-based presentation provides a more intuitive and real-world perspective of who is at risk and also where, which is very important to understand what can be done to reduce risk. So in short, this ERPA risk metric transforms static risk assessments into dynamic, human-focused insights, helping you reduce risk where it matters the most. And we have societal risk as the annual probability that an incident causes multiple fatalities due to the presence of people within the impact area. So it accounts for protective equipment, indoor and outdoor presence, population distribution, and building use. And the results are typically shown as an event curve, which plots event frequency against the number of potential fatalities. This is the event curve obtained as the accumulation of risk at that hydrogen refilling station, which takes into account the different population areas we described earlier. So there was a residential area, apartments, the shop. So it takes into account all that population distribution. How to interpret this graph? Essentially, if the event curve, so the event curve is the red line, if the event curve lies below the guide value, which is the black line, the societal risk is generally acceptable. So if that red line is below the black line, the risk is acceptable under safety regulations. If the event curve lies above the guide value, then the risk is considered unacceptable, which is the case in this situation. And that's where risk reduction measures are required. And also very important to keep in mind that this guide value, the black line, depends on local legislation and may vary by country or region. So like the slope, the starting number of fatalities, the ending number of fatalities, that changes depending on regulation. As I said, in this example, the event curve, the red line, exceeds the guide value. So in this particular case, for this particular hydrogen refilling station, you need additional safety measures to reduce the risk to acceptable levels. However, how can you know where to apply risk reduction measures? And that's where the concept of societal risk maps comes in. So the event curve is a 2D graph. It doesn't give any information about where geographically we can reduce the risk. So to identify where risk reduction is needed, RiskCurves also generates these societal risk maps. They are a geographical breakdown of societal risk, highlighting which areas contribute most to the overall risk. The societal risk area map shows the size and level of risk bottlenecks, whereas the societal risk contribution map shows the cause of the risk bottlenecks. So identifying which locations contribute the most to the overall risk. So this is the societal risk contribution map for the hydrogen refilling station. And the red/orange area over here in the right side highlight the region where the shops are located as a major contributor to societal risk. So in this specific case, we could conclude that it doesn't necessarily mean that the shop must be closed, but it suggests that it's an area worth investigating further. Possible mitigation measures could include reducing the number of occupants, enhancing structural protection, or considering relocation if that is feasible. So this is a very powerful tool for pinpointing risk bottlenecks, communicating risk clearly to stakeholders, and guiding targeted safety improvements. And consequence risk measures the likelihood that a specific hazard threshold is exceeded. In this example, we calculated lethality risk, which is a type of consequence risk that estimates the probability of exceeding lethal thresholds. So that's specifically an overpressure above 300 millibar and a heat radiation above 35 kilobecquerels per meter. So these levels correspond to critical conditions that can cause fatalities. So just to wrap up, conducting a comprehensive QRA using effects and risk curves can enable the evaluation of both consequences and risks associated with hydrogen refueling stations. And I've demonstrated how these tools can simulate a wide range of scenarios and quantify risk using different risk metrics. Just to provide some key takeaways, hazard modeling is a critical part of ensuring safe operations. Accurate assessments require detailed modeling of fires, explosions, and toxic and flammable dispersion. EFFECTS includes advanced tools like 3D congestion modeling, which helps capture the influence of obstructed areas on hazard behavior. And risk curves quantifies risk by integrating failure frequencies, meteorological conditions, and population exposure. Risk metrics like location-specific individual risk and AirPA can support decisions in land use planning and on-site and off-site safety, whereas event curves provide a broader view of community-level risk, where we have societal risk maps to visualize what are the risk hotspots, which can support safety investments and urban planning decisions. So in summary, these software tools can provide a powerful science-based framework to help industries and authorities manage hazards, as well as to improve safety and naturally protect people, assets, and the environment. So that's all for today's session. Thank you very much for your attention. And I hope this gave you a good overview of what are the different hydrogen hazards, and in the context of hydrogen refueling stations, what are the different hazard modeling strategies that we can use to make better safety decisions.